Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about the idea of quantum mechanical superposition. We'll talk about what it means for a quantum mechanical particle to be in a superposition state. And to illustrate this idea, we'll take a specific example. Our quantum mechanical particles will be photons, and the photons can exist in different polarization states. But before we get to photons, let's start off with an entirely classical situation. So we've got some classical light source, and we imagine that that light source is horizontally polarized. So imagine the following situation. I've got some horizontally polarized light, and that light is incident on what is called a polarizing beam splitter. And the polarizing beam splitter has the property that if horizontally polarized light enters it, it will be reflected by 90 degrees. And if vertically polarized light enters it, it will be transmitted. And so we imagine that we take two detectors, one detector which we'll call D sub H, and that's a detector which detects horizontally polarized light, and another detector, DV, which detects vertically polarized light. And so if we shine horizontally polarized light into this arrangement, all of the light will go to this detector, D sub H. And if we were to send vertically polarized light, that is, light that's polarized in the direction perpendicular to the plane of this figure, that vertically polarized light would be transmitted through the polarizing beam splitter and would register on this detector D sub V. So now we imagine inserting a new optical element, a polarization rotator. And the polarization rotator, as the name suggests, can rotate the direction of polarization by some arbitrary angle, which we'll call theta. And the way it works, the way we've defined things is, this is sort of an edge-on view here. So the vertical direction is up out of the plane of the figure. So this figure here shows a positive value of theta corresponds to rotating like so. And we see that theta can vary from plus 90 degrees when the plane of polarization is like this, and then negative values of polarization would be orientations like this, and theta can go all the way down to minus 90 degrees, which is sort of the same as plus 90 degrees of polarization direction like that. And we imagine doing an experiment where we take a pretty bright light source of intensity I naught, and we shine it incident on this arrangement, and we monitor the intensity of light uh, obtained on the different channels, on the horizontal channel and the vertical channel, as functions of this angle theta. And what we find is, this is sort of known as the law of Malou, that the intensity on the horizontal channel will be proportional to the square of the cosine of this angle theta, and the intensity on the vertical channel will be proportional to the square of the sine of the angle theta. And notice that the total intensity, if you add up IH and IV, you get just I naught. So that's a very classical view of what would happen in this situation. Okay, so now let's make a transition from classical physics to quantum mechanics. And the way we'll do that is we'll imagine, instead of having a bright light source, we're going to replace that bright light source with a source of single photons. So, and imagine that these photons are horizontally polarized. So you've got a situation where a single horizontally polarized photon is incident on our arrangement. And let's also imagine that we replace our sort of classical light detectors with things like avalanche photodiodes, which can count individual photons. So if we send our horizontally polarized photon in, and we set the polarization rotator to angle to 0, we'll have a horizontally polarized incident photon incident on the polarizing beam splitter, and 100% of the time we'll get a click on the horizontal channel. So this avalanche photodiode here will register one count for each photon we put in. And similarly, if we set theta, say, to plus 90 degrees, so this horizontally polarized photon gets transformed into a vertically polarized photon, and those photons will pass through the polarizing beam splitter. They'll be transmitted, and we'll get clicks on the vertical channel. So then let's consider what happens if we set the polarization angle on our polarization rotator to 45 degrees, plus 45 degrees. What will we observe experimentally? What we'll find out is that there'll be some randomness. You'll either get a click on the horizontal channel or a click on the vertical channel, and half the time you'll get a click here, and half the time you'll get a click here, but it appears completely random. You can't predict in advance which channel is going to click, but you're either going to get a horizontal count or a vertical count. So the way we can describe this situation quantum mechanically, and we're introducing this notation called Dirac notation here to represent the different quantum mechanical states. So we'll say that in this situation, the quantum mechanical state, which we'll call psi sub plus 45 degrees, which stands for the quantum mechanical state that the photon is in after it's passed through the polarization rotator, we'll say it's in a superposition state of horizontal and vertical polarization. And so it's a linear combination of the two possibilities. And the coefficients out in front here, in this case, would be 1 over the square root of 2 in both cases. And then the quantum mechanical rule for figuring out probabilities is to look at the magnitude of these coefficients squared, and they give the relative probability of measuring different events. So 1 over the square root of 2 squared is a half. So what we have here is a situation in which there's a 50% chance of measuring a count on the horizontal channel and a 50% chance of measuring a count on the vertical channel. Well, where did these factors of 1 over the square root of 2 come from? Well, they really came from taking the cosine and the sine of 45 degrees. So you can think of this, it's a lot like taking components of a vector. The cosine 45 degrees is like the horizontal components of this direction, and the sine 45 degrees comes from taking the vertical component. So more generally, we can write as a function of whatever angle we set our polarization rotator to, the state of the photon when it exits that polarization rotator, we can write as the cosine of theta times this h plus the sine of theta times v. And that works for any value of theta between minus 90 degrees and plus 90 degrees. And so the rules of quantum mechanics are the way we calculate probabilities are to look at these coefficients here. We call these coefficients the probability amplitudes, and the probability of measuring the photon along the horizontal channel is taken by taking the magnitude of the cosine squared of theta, and the probability of having the photon being measured along the vertical channel is by taking the absolute value of the sine squared of theta. And again, notice that if you add up these two probabilities, you get 1, because cos squared theta plus sine squared theta is equal to 1. And that just means that the photon has got to go somewhere. It comes in. Some of the time it goes in the horizontal channel. Some of the times it goes in the vertical channel. So the mathematics of dealing with vectors is actually very helpful in describing quantum mechanical superposition states. So we can draw out this analogy a little bit further. So let me remind you about how vectors work. We have some vector which we'll call A here. And we want to represent that vector in terms of a set of what we call basis states. So we have two unit vectors, a horizontally oriented unit vector, which we'll call x hat, and a vertically oriented vector, which we'll call y hat. And we can represent this vector A as a linear combination of the two basis vectors. So we call this coefficient here the x component of the vector A, and the coefficient that appears in front of y hat we call the y component of the vector A. And notice that our basis vectors, x hat and y hat, obey this property which we call orthonormality. That is, if you take the dot product or the scalar product of x hat with itself, you get 1 because x hat is of unit length and the angle between x hat and x hat is 0. Similarly for y hat dotted with y hat, you get 1. But if you take the scalar product of x hat and y hat, you get 0 because they're orthogonal to one another. The angle between them is 90 degrees. And I'd like you to further notice that the way I can calculate these x and y components of the vector is to take the scalar product of the vector with the corresponding basis vector. So the x component of the vector A can be calculated, that's this length here, can be calculated by taking a dot x hat. That gives you a sub x. And similarly, a sub y is just obtained by taking the scalar product of the vector A with y hat. So as we said, the photon states that we're dealing with after our photon has passed through the polarization rotator, we can describe the photon state as a linear combination of this horizontally polarized photon and this vertically polarized photon. And it really begins to look, the mathematics, if you look at this, really looks very similar to the mathematics of vectors. And what I'd like to do to move the discussion along is to extend this idea of a scalar product into the quantum mechanical realm. So we're going to call the quantum mechanical version of taking a scalar product, we're going to call it an inner product is a more typical name, and we're going to write inner products using this kind of notation. So this notation here is meant to look very analogous to this expression with vectors. So we write the inner product of a horizontally polarized photon with itself in the following way, and that has a value of 1. The inner product of a vertically polarized photon with itself has an inner product of 1, but horizontal photon inner product with a vertically polarized photon gives 0. So these relationships look an awful lot like the orthogonality relationships for ordinary vectors. So now suppose we have a photon in this state psi sub theta, and we want to calculate the probability of measuring the photon in the horizontal channel. Well, we can calculate that probability using the following expression. We're going to call this our probability amplitude, and we take the absolute value of that probability amplitude and square it to get the probability of getting a photon measured in the horizontal channel. So to see what I mean by this, let me write it out. So I'm simply substituting in for psi sub theta this expression here. So plugging in here that expression. And this is the expression that I want to evaluate. And I'm going to take advantage of these orthogonality rules here. So the inner product of H with H is 1, but the inner product of H with V is 0. So I can write that the probability of measuring a photon on the horizontal channel, I get a cosine theta times 1 here, and a sine theta times 0. And so the probability of getting a measurement on the horizontal channel is the magnitude of cosine theta squared. And similarly, it's easy to see that the probability of measuring the photon going to the vertical channel is we just take the inner product of the V basis state with psi sub theta and that's going to give a sine squared theta. So this is a nice way of doing these calculations, and you'll see that when we get to more complicated situations, relying on this kind of mathematical technique will make coming up with actual predictions of probabilities much easier once you get used to this. So we'll see that in the next episode of What's the Big Idea? Hope to see you again soon. Bye bye.